Okay, so today I'll be solving this problem, which is today's POTD, and today is 11th of October. So this POTD is maximum total damage with spell casting. So what we basically have to do in this problem is a magician has various spells, and we are given an array power where each element represents the damage of the spell, and multiple cells can have the same damage value. So it is a known fact that if a magician decides to cast a spell power of I, then he cannot cast the spells power of I minus 2, power of I minus 1, power of I plus 1, and power of I plus 2. So what we have to do is basically each spell can be only casted once, so we have to return the maximum total damage that we can do by casting spells in such a way that the answer of damage is maximized. So yeah, we have to do that. So for example, in this case we can choose them like 0 1 3, so it would be 1 3 and 0 1 1 and 4. So these conditions satisfy this condition because let's just say that if we decide to cast 1, then we are not casting minus 2 or 0 or minus 1, or we are also not casting 2 and 3. So we are only casting so this set basically is following all these conditions, and similarly in this case this set is following all these conditions. So basically one thing that we can think about it. Okay, so now coming to the problem, I solved it, but I'm just going to explain it how I did. So one thing we can think about the problem is that the conditions that we have, the 4 conditions that we have here, they basically translate to something like this in a sorted array. So when we think about it, we know that ai is less than equals to ai plus 1 is less than equals to ai plus 2. So in sorted array, what happens is that this condition will follow. So we know that we don't really have to check for these conditions, because let's just say that we decide to choose we go in certain value. Let's just say that it's a of I plus k, and if you're deciding to choose a of I plus k, then looking back, we have choices that start from ai plus k minus 3, so we can choose all of these, and we can choose the maximum value for if you decide to choose this. And if you don't decide to choose this, then we can just take the result from the previous iteration. But the thing about not caring about these values is because when we go ahead in our array, we will definitely not choose we will definitely not include a of I plus k in a of I plus k plus 2, because we always check that this value should be less. This value, the values that we are selecting prior to this value, should always have an absolute difference that is of minus 2, that is of less than minus 2. So we will never choose this, because we will see that okay, a of I plus k plus 2, if we are trying to select it, then we will not choose a of I plus k plus 1, and we will also not choose a of I plus k. So we'll choose only starting from a of I plus k minus 1. So this condition becomes it becomes something that we don't have to check if the array is sorted. So first thought that I had was to sort the array so that I can not care about all these conditions, and I can only check for monotonically decreasing conditions, that are these 2. So what I did then was since we had to check the element that was prior, and it had to be less than or equal to p of I minus 3. So this condition is basically translating to okay, my the element that I'm selecting is less than equals to the current element minus 3, because these are the values that we can choose, removing these 2. So this is what I'm checking here. And so basically what I did was but we can also have these iterations can be O of n when we have a certain element that is let's just say that currently we are choosing an element which is 3. So let's just say that we have an element 2 which occurs a lot of times. So let's just say that the position that this element occurred in was, let's just say it was, I don't know, 100, and then we have 2 occurring from basically 3 till 99. So then we'll just waste our iterations and this will become O of n square. So what I did to counter that was I created a map that stores the frequency of all the elements that are present in the power, and then I created an array p2 which basically stores all the elements in the power in a sorted order, and then I resized p2 in such a way that it only consists of the unique elements. So now let's just say that in this case, if we have 1 1 3 and 4, now first of all I'll sorted them so it will remain the same, and then I'll just have 1 3 and 4. So in this case what happens is that we only have to check at most 2 elements, because then we'll eventually reach at an element that is less than or equals to the current element minus 3, and then we'll just break out the loop. So what I'm doing is I'm iterating through the entire array. I hope this is clear. What I did here, this was just an optimization so that our code can run faster. So what I did here was I created a DP and a maximum array. So the maximum array basically stores all the so max of I is basically the maximum of dp of I till the ith index. So what I did was basically I iterated for the last value, and then I checked if the current value is less than or equals to the current element minus 3. So what I did was I just added the maximum dp that we have seen till the jth index, and then I just break out of the loop because we have already found out the maximum element. And then I was updating my maximum array in such a way that okay, I will store the current dp as a maximum value if and only if the previous maximum value is less than the dp of I. So basically I just stored for every maximum value the maximum dp of I that we have till that index, and then I can just return the maximum index of n minus 1. So yeah, so that is how we do it. We can also do one thing that we can directly here we can directly do something like dp of I minus 1 comma dp of I. We can also do this. I believe that we can do this because yeah, I think we can do this. This is just an optimization on the space complexity, so this is something that I'm learning on the go too. So yeah, so I think I can check if I can do this. So I'll just do this and this, okay, and we can just do it dp. So let's just check if we can do this or not. Okay, I'll just submit it and see. This actually improves our space complexity overhead, and it actually works. So that maximum array was actually not required because we are always updating the dp anyways. So yeah, we can just do this. So I think this is it. This was a problem. I think the main part of it was identifying that these two values don't matter, because if we try to check for these two values, then our code will become pretty messy and it would become confusing. So the most important part was identifying that this is what we don't really care about if we sort the array. So we sort the array, and then another optimization was using map to reduce the size of the array so that we don't have to iterate for all the elements. And then we can just use our dp of I to update we can use dp of j to update the current state of dp of I, and we can also always keep the maximum value in the current dp of I, because that is what we care about when we reach a state j that satisfies this condition. So yeah, that is all for this problem. This was a good problem. I think it was a nice introduction to dp problem, and I think yeah, this can be done. It was a pretty nice dp problem, but not that hard, but it is something that can form a very good base for dp. So yeah, I hope you enjoyed it. Yeah, this problem was great.